Our next layer of real numbers that we're going to dive into are rational numbers. And again, we have real numbers and rational. So unfortunately, I can't use R to represent rational. So instead, we use a Q. Okay? Because really, it comes from a quotient. So if you think about this, a rational number is going to be something that can be written as a fraction, where these two values, A and B, are integers. So a rational number could be written as an integer divided by an integer. So to give you some examples, -3/4 is a rational number. And this does divide nicely as a decimal. It's 0.75 and negative. If you have 1/3, if you plug that into your calculator, it's not as nice, but it's 0.33333333. So it's 0.3 repeating. And then really you have all of your whole numbers, natural numbers, and integers. They are rational numbers. Because if you think of the number 5, well, you can write this as -5 over +1. So you can write it as an integer divided by an integer. So really, every single integer is a rational number. Every single whole number is an integer and a rational number. And every single natural number is a whole number, an integer, and a rational number. Okay. So there is a distinction for rational numbers, and then our next section, which is irrational. You can have decimals for these, but it needs to be a terminating decimal, meaning it stops, or it needs to be a repeating decimal. If it doesn't terminate or it does not repeat, it is not going to be a rational number. Now, what we typically like is the simplest form for a rational number, because again, there's lots of ways that you can write the same number. If you take a half, it's the same thing as 3 divided by 6. So we want the simplest form. So we say a rational number is reduced or simplified if there's no common divisor in the numerator and denominator other than the number 1. So let's just try a couple examples of this. Again, you don't need to find the biggest number that goes into it. You just need to start dividing. So let's start with 12 over 20. Well, maybe I notice they're both even, so I go ahead and divide top and bottom by 2. 12 divided by 2 will give me 6. 20 divided by 2 gives me 10. And then I notice, oh, okay, they're still both even. So let's go ahead and divide by 2 again. That gives me 3 in the top and 5 in the bottom. And then unfortunately at this point, 3 and 5 are prime numbers, so there's definitely no way I can simplify this further, okay? So realistically, instead of doing this in 2 steps, really, both of these are divisible by the number 4. That's the biggest thing that divides both. So if I take the top and divide it by 4, that gives me 3. The bottom divided by 4 gives me 5, okay? But it's not necessary to reduce something. You can take it piece by piece instead. So in this next example, if I have 132 over 144, well, I could sit here and I could try a bunch of stuff, but I notice right off the bat they're even. So let's go ahead and divide top and bottom by 2. So you can follow along in your calculator. I'm not going to at this stage, but 132 divided by 2 will give me 66. And 144 divided by 2 gives me 72. And then here again, they're both even. So we can divide by 2, which means really I could have divided by 4 at the start and saved a little work, but that's okay. Dividing by 2 gives me 33. Dividing by 2 gives me 36. And then I can keep going. These are actually both divisible by 3. So it's kind of like you're finding the prime factorization for both of these, but you're just utilizing that to simplify. So if I divide top and bottom by 3, that results in 11 over 12. And then at that point, 11 is a prime number, so there's nothing I can do here. So really, instead of doing 3 pieces, if I multiplied these out, 2 times 2 is 4 times 3, really these are both divisible by 12. So I could have done it in one swoop instead. All right. So within these, since we have these rational numbers, we know that we've seen stuff like 73 over 9. That could be something that opens out. So 73 can be divided partially by 9, but there ultimately ends up being a remainder. So when you have something of this form, there's 2 different ways that you can express it. The first is a mixed number. The second way is an improper fraction. And so we're going to work on going back and forth between these. So a mixed number is the sum of an integer and a rational number. So what you would see is you have a whole number, and then you have a fraction, 3/4. So all this means is you have 3, and then you have 4/7. Okay? I definitely think I said that wrong, so sorry if those words came out or the numbers came out differently. But 3 and 4/7 is really the number 3 plus 4/7. You do have to be a little bit careful of splitting it like this though, because if I say -3 and 4/7, really it just means the minus sign is on the outside. So it's just overall a negative number, but it's 3 plus 4/7, and then you apply that minus sign. So this is one way you can display a rational number. The more common way that you're likely used to is improper fractions. So an improper fraction is a rational number whose numerator is greater than the denominator. So basically it means the denominator will divide into the top, but there's a remainder that's going to be left over. So if you think 19 divided by 5, that's a clear-cut number, but you are able to turn this into a mixed number. So if I look at this, 5 goes into 19 3 times, because that gives me 15, and then there would be 4 left over. So this is the same thing as 3 and 4/5. Okay. Another example is 24 divided by 7. Well, in that case, if you tried to plug that into your calculator, you'd get 3 point something. So 7 goes into 24 3 times. And if you do that, 7 times 3 is 21. There is 3 left over. So that would be this mixed number. And then finally, if you take -30 and divide it by 29, well, overall, this number should be negative. 29 goes into 30 once, and there is a single number left over. So 1 out of 29 is left. Okay. So you can always take an improper and make it a mixed number. If I want to do the opposite, if I want to go from mixed to improper, I really am kind of doing the reverse of this process. So ultimately, you can break this down in the same way I showed you before. So up here, you would have 3 plus 4 over 7. Well, to be able to add those things, you need to find a common denominator. And the way you do that is you would have to have a 7 in the bottom. So that means you need to multiply by a 7 in the top. So you're going to multiply the integer by the denominator of the rational number, and then you're going to add it to the numerator of the rational number. So just as 2 examples to show you this, if I have 2 and 1/9, this means I'm really taking the number 2 and I'm adding 1/9 to it. To get these to be the same denominator, I need a 9 in the bottom, which means I need to do the same thing in the top, okay? So 2 can really be written as 18/9, and then we go ahead and we add 1/9. And the way we add fractions is we just add the numerators, the denominator, absolutely nothing happens to it. So really, this is going to be 19/9 as an improper fraction. Okay. If I want to do this next one and I have this minus sign, you have to, again, be careful. You do not want to write this as -8 plus 3/4. That's going to give you a different answer. Instead, just overall, this thing is going to be negative. So we'll do the 8 plus 3/4 separately, and then we tack on that minus sign. The other way you could think about this is just go ahead and do this piece and then apply the minus sign. So I'll show you it this way, and then I'll go back to the top. In this case, this is 8 plus 3/4. I need to get a 4 in this denominator, so that means I need to put a 4 in the numerator. 8 times 4 gives me 32. So I need 32/4 plus 3/4. And then we go ahead and we just add the numerators, and the denominator stays untouched. So this would be 35/4. And then what that means when I apply that minus sign is it's just negative 35/4. Okay. So again, just be cautious of that. But just to show you, this results in the same thing. Really, you do the same process. You need a divide by 4, so you times it. So you get 32/4 plus 3/4. And then adding those together gives me 35 in the top and a 4 in the bottom. So just ignore that minus sign until the very end, okay? So the very last thing we're gonna do in this section is talk about expressing decimals, which are either terminating or repeating, as a rational number. So terminating decimals, if you think about this, really every single decimal place corresponds to a tens position. So your tens in general are just 10. Then you have your 1 spot. If I even go this way, my 100th spot is my 3rd position. Well, when you get to decimals, it's the same thing. Tenths is 1/10. Hundredths is 1/100. And thousandth is 1/1,000. So really, if you plug this into your calculator, 1 divided by 10 gives you 0.1. That's 1 decimal place for tenths. Hundredths is like pennies. You have 100 pennies in a dollar. So it's the 2nd decimal place. Thousandth is 3 zeros. It is the 3rd decimal place. Okay. So what we're going to do, if I want to express a terminating decimal as a rational number, all you're going to do is focus on how many decimal places, and that's going to tell you what the denominator should be, okay? And then in the end, I want to go ahead and reduce it as much as possible. So if I look here, I go to a single decimal place, and if I match that up, that deals with the 10 spots. So all I'm going to do is I'm going to take the digits I see, and I'll divide it by 10. So my digit in this case is 9. So I do 9 divided by 10, okay? So a single decimal place means I have a single 0 in my bottom. Then again, you could plug this into your calculator, but 9 divided by 10 does indeed give you 0.9. To show you, if I plug this into the calculator, 9 divided by 10 does give me 0.9. Moving on to this next one, it's 2 decimal places. So that means it's going to be out of 100. And all I do is I take those significant numbers and I divide it by 100. So if I plug that into my calculator, 49 divided by 100 indeed gives me 0.49. And again, this does say to reduce to lowest terms, and although I didn't show that, well, 9 and 10, absolutely nothing divides either of those. Same thing, 49 over 100, not even numbers. You can see 49 only is divisible by 7 and 7, really. So if I try to divide it by 3, nothing happens. It's only divisible by 7, but 100 is not. If I try this next one, 0.048, this is the thousands position. So 3 decimals mean I put 3 zeros in the bottom. And again, that means I'm just going to look at those significant numbers, which are 0, 4, and 8. The 0 is not significant, so I'm really just going to take 48 and divide it by 1,000. And to show you, 48 divided by 1,000 is indeed 0.048. Now, unfortunately, this 48 and 1,000 are both even numbers, so this I can actually simplify. So here, top and bottom are even, so we can reduce by dividing by 2. 48 divided by 2 will give me 24. 1,000 divided by 2 gives me 500. And then, well, those are both even, so I can do this again. Divide by 2, divide by 2. That gives me 12 in the top, 250 in the bottom. And then here, those are both even again. So I can keep going. Divide by 2, divide by 2. That leaves me with 6 in the top and 125 in the bottom. Well, at this point, 6 isn't divisible by much, so it's divisible by 2, but 125 isn't. 6 is also divisible by 3, but 125 isn't. So this is as reduced as I possibly can get it. And just to check my answer, if I do take 6 and divide it by 125, I get exactly 0.048. So same thing, just reduced.